Welcome back to Arxflix. Today, we're diving into a paper that tackles the challenge of building efficient large language models, LLMs, for mobile devices. This research, titled MobileLLM, Optimizing Sub-Billion Parameter Language Models for On-Device Use Cases, explores the design and implementation of LLMs with fewer than a billion parameters, making them suitable for deployment on resource-constrained devices. This figure highlights the performance of different LLMs with less than a billion parameters on zero-shot, common-sense tasks. The size of each bubble represents the model's size, and the results show that MobileLLM outperforms previous models in this category. The paper argues that while large LLMs like Chat-4 are powerful, their size and computational demands make them impractical for widespread mobile deployment. The authors highlight the limitations of mobile device memory and battery life, emphasizing the need for smaller, more efficient models. This figure illustrates the memory hierarchy in mobile devices, where DRAM, with limited capacity, is crucial for high-speed applications. The authors argue that sub-billion parameter LLMs are a practical choice for mobile deployment due to these memory constraints. The paper makes several key contributions to the field of sub-billion parameter LLMs. They demonstrate that depth is more important than width for smaller models, meaning deeper architectures with fewer layers are more effective. They also revisit embedding sharing techniques and implement grouped query attention to maximize weight utilization. The authors introduce MobileLLM, a strong baseline model for sub-billion parameter LLMs. They achieve this by incorporating several design techniques, including 1. Swigglue feed-forward network. They use the Swigglue activation function in the feed-forward network, which improves performance compared to traditional ReLU activation. 2. Deep and thin architectures. They emphasize the importance of depth over width, showing that deeper models with fewer layers perform better. 3. Embedding sharing. They revisit the concept of sharing input and output embeddings, reducing the number of parameters and improving efficiency. 4. Grouped query attention. They utilize grouped query attention, a technique that reduces redundancy in key-value heads and further optimizes weight utilization. This figure shows the design roadmap of MobileLLM, highlighting the improvements achieved through each design technique. The authors demonstrate consistent improvements for both 125M and 350M parameter models. The paper introduces a novel technique called immediate blockwise weight sharing. This technique shares weights between adjacent blocks in the model, reducing memory movement and latency overhead without increasing model size. This figure shows the performance of different model architectures on various tasks, demonstrating the superiority of deeper and thinner models. The authors highlight the importance of depth for sub-billion parameter LLMs. This figure presents an ablation study on the number of heads and key-value heads in the attention mechanism. The results show that using 16 query heads and reducing the number of key-value heads to 4 achieves a good balance between performance and model size. The authors introduce MobileLLM, a model that incorporates layer sharing, achieving further accuracy gains over the baseline MobileLLM. This model demonstrates the effectiveness of their proposed weight sharing technique. This paper makes significant contributions to the field of sub-billion parameter LLMs, demonstrating the importance of architectural design for smaller models. MobileLLM and MobileML set new benchmarks for accuracy and efficiency in this category, paving the way for more practical and widespread deployment of LLMs on mobile devices. Thanks for watching. Don't forget to like and subscribe to Arxflix for more summaries of cutting-edge research in deep learning. Thanks a lot to Element for supporting Arxflix and providing this wonderful voice.